The second part is continuity. First, the definition of continuity at a point. So basically, this is the equation, and talk about the definition. And if you say it in words, is the two-handed limit is equal to the actual value, actually y value when x equals to approaches c. So let's draw a graph so we can know it better. And this is c. Let's say the graph look like something like this, and let's see the point around x equal to c. They are all like from the two sides, they are both approaching the actually y value when x equals c. Then it means the function is continuous at point c. Then let's move on. However, there's sometimes a function only can be approached to its y value on one side. Let's see this right here. So the left side, the point is approach the y value when y equals x1. So this is actually approaching f of x1. However, this point on the right side are not. So it's only continuous at left endpoint. Because this is left side, so it's only continuous at the left endpoint. So for this one, it's easy to see. It's continuous at the right endpoint. However, if we only see a part of this function, let's say this part, every single point, the function is always continuous in any single point in between this interval. It means in this interval, the function is continuous. If you want the whole function be continuous, it has to be every single point in the domain of the function is continuous. So let's see if this is y equals x. Let's go here. It's easy to see every single point in the domain of this equation is continuous. This is the continuous function. This is an example of that. Interval of continuity. So this is a practice I want you guys to do. So you can pause and try to solve it by yourself. And I'll write the answer down here. Really be careful with the parentheses and bracket. It really depends on like where the holes are. And these are some properties of continuous function. Just remember them. And a better way to remember them is like always refer to them when you do your homework. That will help you really remember it. And now the intermediate value theorem. So basically what it's talking about is, let's see, if f of a is less or equal to f of b, and you want to find any value, no, we should not write this way. Let's say any y in between this, you can always find the y, you can always find this y of f of c, where c is in between a and b. So basically, let's see how to prove this theorem. If this is f of a, this is f of b. Let's see, if we want to get this point to this point, we have to go through every single different height in between them. No matter which way you are going, you will of course pass all the y value in between them, or else you will not be continuous. And also this intermediate value theorem only can work in continuous function. Oh, also it can work if the function is continuous in this interval here. How do I spell this wrong? Never mind. The last part is discontinuity. There are different kinds of discontinuity. So first one, let's see. The example here is continuous. Let's try to change this to a discontinuity. Let's paste it here. First one, removable discontinuity, which means there's a hole in any part of the function. Let's see it here. Let's just pretend it's a hole. So when we get to this part of the function, suddenly it's just not connected together. So this is called removable discontinuity. Second one, jump discontinuity. Compared to this graph, it not only has a hole in anywhere, and it has, like, when x equal to this, it actually has a y value, but it's not its limit. This is jump discontinuity. Infinite discontinuity, actually we cannot refer to this graph here. Let's draw another graph. Actually, an infinite discontinuity basically means there's a vertical asymptote, I think. Oh my god. Let's see if a function is like this. We can easily see when x equal to 0, it does not have a limit because the two sides are not connected together because there's a vertical asymptote in between them. So this is called infinite discontinuity. The last one is oscillating discontinuity, which is like this. Let's still see when x equal to 0, the graph will look like this. This is an example. So we can see, like, it's really hard to find the limit when x equal to 0. Because no matter how close we try to find a point close to 0, we can always find value like varied. We can never tell actually how the point get to a value because they are like going up and down, like in a really frequently, so we cannot tell the limit of x equal to 0. This case is called oscillating discontinuity. And that's all for chapter 2. So this is the PDF link of my notes. You can always refer to it if you want to. And also, thanks for watching.